All right, let's dive right in. Today, we're talking about a really powerful idea in the world of AI. Why a whole team of models almost always beats a single lone genius. It's all about teamwork.
So, first things first, let's set the stage with what I call the one model problem. This is really about the trouble you can get into when you rely on a single, so-called lone genius model. Just think about it for a second. If you had a really complex problem to solve, would you put all your faith in one single expert, no matter how smart they are? Or would you rather have a team of experts who can look at the problem from different angles? Well, that's exactly the kind of dilemma we face in machine learning. And here's why that's such a tough spot. On one side, you have models that are just too simple. We say they have high bias. They kind of paint with a broad brush and just miss all the important subtle details in the data. But if you go to the other extreme, you get a model that's way too complex. This one gets lost in the details. It essentially memorizes the data it was trained on, including all the random noise, and then when you show it something new, it completely freaks out. We call that overfitting. So finding that sweet spot in the middle, that's the real challenge.
So, if that lone genius model is always walking this tightrope, what's the answer? Well, this brings us to a really beautiful concept, the wisdom of the crowd. We're going to talk about ensemble models, which are basically the AI version of teamwork. At its core, the idea behind an ensemble model is actually pretty straightforward. Instead of trying to build one giant, perfect model, you build a bunch of smaller, simpler models. We call these base models. Then you just combine what they all think to get one final, super strong prediction. It's all about leveraging collective intelligence. Okay, let's make this real. Imagine we're trying to diagnose hepatitis C. Our first model has a very simple rule. If a patient's albumin level is below 35, it's a yes. Our second model also has a simple rule, but it looks at cholesterol instead. Now, either one of these models by itself could easily be wrong, right? But the ensemble model puts them together. It creates a new, stricter rule. It only predicts hepatitis C if both of those conditions are true. By combining their simple perspectives, you get a much more reliable and nuanced decision. So how do we actually put these AI teams together? Well, it turns out there's more than one way to do it. Think of it like a playbook. And we're going to walk through the 3 most popular strategies for building your AI team. Okay, strategy number 1 is called boosting. The best way to think about this is as the incremental improvement team. It's a group that learns from each other's mistakes one after another. The key word for boosting is sequential. Here's how it goes. You start with a pretty simple, weak model. It tries to make predictions, and of course, it gets some of them wrong. Now, for the next model in the sequence, you basically say, hey, see all those spots where the first model messed up? I want you to focus on those. You do this by making those mistaken data points more important or giving them more weight. This forces each new model to become an expert on the errors of the model that came before it. You just keep repeating this with each new model fixing the last one's mistakes until the entire team is incredibly accurate. So the upside here is pretty obvious, right? Boosting is relentless. It hones in on the weak spots and gives you a final model with very low bias. But what's the catch? Well, the downside is built right into the design. Because it's sequential, one model has to wait for the previous one to finish. You can't do it all at once. It can be slow. Plus, if one of your early models is just really bad, it can send the whole team off in the wrong direction, focusing way too much on the wrong kind of errors. All right, next up we have bagging. And yeah, that's its real name. It's short for bootstrap aggregating. I like to call this the wisdom of the crowd team. Unlike boosting, this approach isn't about learning in a line. It's about working in parallel and then taking a democratic vote. Okay, so here's the game plan for bagging. You start with your big data set. Then you create a whole bunch of smaller, slightly different random subsamples from it. Think of it like taking a huge population and creating 100 different focus groups. Then you train the same kind of model on each of those unique little data sets, and you do it all at the exact same time. When you need to make a prediction, you just ask the whole team for their opinion. If it's a yes or no question, the majority wins. If you're predicting a number, you just average all their answers. Simple as that. The huge win for bagging is speed. I mean, since everything happens at once, it's incredibly efficient. It's also fantastic at preventing that overfitting problem we talked about earlier because all the little differences in the models tend to cancel each other out. The main drawback? It might not be quite as good at reducing bias as boosting is. And of course, if the type of model you chose to begin with is just a bad fit for the problem, then the whole team's performance is going to suffer. And that brings us to our third and final strategy, stacking. This one is my favorite analogy. Think of it as the diverse council of experts. Here, you're not just using a team of identical twins, you're bringing together a bunch of different specialists, and then you're hiring a manager to listen to all of them. Stacking is a really cool two-level process. On the first level, you train a bunch of completely different kinds of models. Maybe you train a decision tree, and a logistic regression model, and something else, all on the same dataset. Then, and this is the genius part, you take the answers from all of those different models and you use them as the input for a brand new model on the second level. This final model is called a meta model, and its only job is to learn how to best combine the opinions of all the experts on its council to make the final decision. It learns who to trust and when. Now, the payoff for all that extra work can be huge. Stacking can achieve insanely high accuracy because it literally learns how to balance out the weaknesses of one model with the strengths of another. But, you guessed it, there's a trade-off. It's way more complex to set up and to understand, and its success completely depends on you picking a good, diverse council of experts to begin with. All right, that's enough theory. Theory is great, but let's see how these strategies actually perform in the real world. So, for a bit of fun, welcome to the Bob Ross paint-off, where we're going to use these models to analyze the work of a legend. You know, as the man himself said, we don't make mistakes, just happy little accidents. And honestly, that's the perfect way to think about machine learning. Every little error is just an opportunity for the model to learn something new. So here's our challenge. We went through the data from every single episode of The Joy of Painting, and we found something amazing. Get this, a staggering 89.5% of all his paintings have at least one happy little tree in them. So the job for our AI models is to predict, based on everything else in the painting, whether a tree is going to show up. And here are the results. We put a boosting model up against a bagging model. And what happened? A dead heat, a perfect tie. Both models achieved an accuracy of 92.6%. They were both incredibly good at figuring out if Bob Ross was going to paint a tree. So that begs the question, what do you do when performance is exactly the same? And that question brings us to our final and maybe most important takeaway. When accuracy is a tie, how do you pick a winner? This is where we really get to the heart of why ensemble methods are so practical and powerful. The tiebreaker is one simple word, efficiency. Remember, boosting is sequential. It has to train one model, then the next, then the next. It's the tortoise. Bagging, on the other hand, is parallel. It trains all of its models at the exact same time. It's the hare. Now, on a small dataset, who cares? But when you're dealing with massive amounts of data, that difference in speed is, well, it's everything. So even with identical accuracy, bagging is our clear winner in the real world. Okay, so let's wrap this up. What are the big ideas to take away here? First, and most importantly, don't put all your eggs in one basket with a single lone genius model. Ensemble models, which combine multiple simpler models, are just stronger and more reliable. We talked about three main strategies. There's boosting, which learns from mistakes one step at a time. There's bagging, which is like a democratic vote from a team working in parallel. And finally, there's stacking, which uses a smart manager to combine the strengths of different kinds of experts. It's all about making the whole greater than the sum of its parts. And that leaves us with one last thing to think about. We've just seen how a team of relatively simple models can tackle some really interesting problems, from medicine to art. So that leaves me wondering, if these teams are this powerful now, what kind of massive complex problems could a team of advanced AIs solve for us next? Thanks for tuning in.